Good evening to Dr. Mas Nizam and Dr. Ikman Isha. Today I'm going to present about this project about design, improvement and analysis of aircraft engineering bracket. My part is thermal stress analysis. In this project, we have drawn three types of design, and the design we chose is design 3. This design was done by myself, and the material we use is aluminum alloy 7050/G7651. The mass of this project is 0.73 kg. So in the thermal analysis, the focus was on understanding the effect of the temperature on the structural model. The study explored three key outcomes: equivalent stress, factor of safety, and total deformation. These results are crucial for evaluating the structural integrity and performance of the model under thermal loading condition. By comparing the stress and deformation value between models with and without thermal change, we are able to understand how temperature variation influence mechanical behavior. For this analysis, an initial temperature was set at 25 Celsius and the final temperature at 150 Celsius. Both these temperature were taken from the internet, from the reference of the internet. So let's go to the result. First is about the equivalent stress. When considering thermal effect, the maximum Mises stress observed is 1135.5 MPa. As shown in the diagram, uh, right around in the top surface of the hole, indicating the region experience the highest stress concentrated due to the force applied in and thermal effect. The minimum one stress is 1.2136 MPa, shown in dark blue, located at the central body of the part, representing the region experienced the least amount of stress. As the color transition from green to yellow, the stress level increase moderately, indicating regions under moderate stress. The gradient help in identifying how different area of the model respond to the thermal change. Next is thermal stress analysis. Reveals a maximum deformation of 0.49 mm in the engine bracket, which is highlighted in red. The highest deformation is observed at the top cylindrical features of the component, indicating significant structural displacement in these areas. Conversely, the minimum deformation is zero, shown in the blue, and is found at the base of the engine bracket, signifying that these parts of the structure remain relative. Underform under thermal stress. The color range from orange, yellow, and green at the central body of the part. These represent intermediate level of deformation, indicating region under moderate deformation. Next is safety factor. As you can see in the diagram, most of the base part are red, which is unlikely to fail. This design unlikely to fail under the apply force, and the orange and green region with the safety factor between 4.1 and 11, indicating a moderate safety margin. The minimum safety of this factor is 0.43. Just now I tell you that the under base is marked in red, which means this part of the structure uh, under the highest stress relative to their strength. So the low safety factor suggests that this region are the weakest point structure when the subjected thermal stress. So compared to comparative analysis of stress and deformation due to impact of thermal. So with and without temperature. So the stress dramatically increase. With the temperature is 1135.5 MPa. Without is 167.26. The thermal effect significantly evaluate stress level in the structure. Substantial increase from in total deformation with the temperature is 0.49 mm, without the temperature is 0.17 mm. Implication deformation triple due to thermal changes. The cause of increase are due to the additional strain and force from the thermal expansion. Next is discussion. uh, Discussion is a factor that contributing to result. Thermal expansion, material expand or contract with thermal changes. Aluminium alloy 7050T7651 has a specific coefficient of thermal expansion which is 2.36 exponent negative 5 Kelvin, leading to thermal stress when the bracket undergo temperature variation. Material property. The yield strength and the Young modulus of the aluminum alloy at the different temperature affect how the bracket respond to the two thermal loads. The material's ability to withstand stress without significant deformation is critical. Tendency of the bracket failure without the FOS is calculated to be 2.9, indicated the low tendency of failure. However, with thermal effect, the stress increase significantly and FOS to drop 0.43. These evaluate stress reduce the FOS dramatically, indicating that the bracket is likely to fail under thermal condition due to combined effect of mechanical and thermal loads. The material selection of aluminum alloy 7050/T7651 for the bracket was based on its highest strength to weight ratio, good machinability, and corrosion resistance. However, thermal stress analysis reveal a significant limitation due to its high coefficient of thermal expansion. When exposed to thermal fluctuation, the alloy undergoes substantial expansion and contraction, inducing significant thermal stress. This results in the drastic reduction in the factor of safety from 2.9 without thermal change to 0.43 with thermal effect, indicating a high likelihood of failure under thermal condition. Despite its mechanical advantage, the material thermal expansion characteristics make it less suitable for environment with significant temperature variation, necessitating a reconsideration of the material choice for such application. Conclusion. Uh, the thermal stress analysis of the aircraft engine bracket revealed critical findings. Maximum von-Mises stress peak at 1135.5 MPa around the whole surface, uh, contrasting sharply with minimum stress of 1.2136 MPa at the central body. Stress concentration visually mapped through a color gradient from green to yellow, indicating various stress levels across the structure. Safety factor range from robust dark blue to critical low rate at 0.43, highlighting the area of the strand vulnerability respectively. The choice of aluminum alloy 7050 T7651 price for its strength to weight ratio and machinability face limitation due to high coefficient of thermal expansion. These characteristics induce significant thermal stress, notable reducing the safety factor from 2.9 to 0.43 under the thermal cycling. Consequently, reconsideration of the material is recommended for environment with pronounced temperature variation. This study underscore the imperative of comprehensive material analysis, particularly accounting for the thermal effect to ensure the reliability and safety of the aerospace components. Thank you.